Hello, ladies and gentlemen, and welcome back to the 11th episode of my online course on special relativity. My name is Andrzej Dragan. I'm a professor of theoretical physics at University of Warsaw and National University of Singapore. And today we'll attack one of the hardest and less known problems in special relativity, namely a fact that a composition of two Lorentz transformations is not just another Lorentz transformation, but that there is an extra rotation involved. That extra rotation is usually called a Thomas-Wigner rotation, but the irony is that it has already been discovered and described many years before that by a Polish physicist, Ludwig Silberstein. In his textbook, published in 1914, he says that a composition of two Lorentz transformations for non-parallel velocities v1 and v2 is not again a single Lorentz transformation, but it is composed with a certain rotation. Hence, it would be more appropriate to call it a Silberstein rotation. And today we will try to understand how an object rotates in space when its velocity changes in time. So let us begin by reminding ourselves about the terrible-looking formula for the velocity transformation between two inertial observers, but for a general three-dimensional case. These two observers, A and B, are in a relative motion, so that B moves with velocity capital V relative to A, and they both watch the same witch flying on a broom, and that broom moves with velocity small v relative to A, and with velocity v prime relative to B. And our formula captures the relation between those three velocities, v, v prime, and capital V. And we will consider a slightly different scenario in which B is moving with a constant velocity small v relative to Alice, and then suddenly it changes that velocity by an infinitesimal amount, and that new frame of reference we will denote as B prime. So that instead of moving with velocity v, it will move with some new velocity v plus dv. And that new frame of reference B prime will move relative to B with some infinitesimal velocity that we'll denote with dv prime. So in the previous episode, we have already justified that if B is unrotated relative to A and B prime is unrotated relative to B, then in general, B prime is rotated relative to A. So that the velocity of A relative to B prime is not minus V minus dv. So we will now investigate what exactly is the angle of rotation between B prime and A. Usually this problem is considered to be too hard for regular textbooks, and if any author ventures into its derivation, it usually involves many pages of painful calculations and a repertoire of technical terms such as zero groups or zero vector spaces, associative commutative groupoids, holonomic transformations, Clifford algebras, or tetrad formalism. We, on the other hand, will do neither of these things. And we will derive our effect within only 3 lines, using only basic vector operations. But there is a price to be paid. We have to be smart. So people usually derive the angle between B prime and A, which is hard. But we can notice something clever. That extra rotation is only present because of relativity. So if the speed of light was infinite, that rotation would not exist. So that angle of rotation is also the angle between B prime and its non-relativistic approximation. This angle of rotation that appears in the double Lorentz transformation is in fact the angle between B prime and its non-relativistic version, in which B prime is simply moving with velocity v plus dv prime. And since the angle in question is infinitesimally small, we can represent it with a cross product between the vector v plus dv and its non-relativistic approximation v plus dv prime. And since the cross product of any vector with itself vanishes, this expression simplifies to the following one. And all that there is left for us to do is to express dv prime in terms of v and dv. And this can be easily accomplished by simply using our nasty formula with interchanged velocities. So instead of capital V, we will substitute small v. Instead of a small v, we will use v plus dv. And instead of v prime, we will have the unknown dv prime. And after substituting all that into our nasty formula, we get the following even more ugly expression. However, this expression will greatly simplify once we consider the cross product between v and dv prime. Most of the terms in our terrible expression simply go away. And all that we are left with is a very compact and simple formula. And after plugging it into the expression for the angle of rotation and dividing by dt, we obtain the rate of rotation of a frame moving with arbitrary velocity v and arbitrary acceleration dv over dt. This effect is known as Thomas precession. Thomas precession spins around any object that changes its velocity. And that purely geometric effect has been accidentally discovered experimentally by Thomas, who investigated motion of electrons around atoms. I discuss all these things in more detail in my textbook on relativity, which is called Unusually Special Relativity. Check out the link in the description. And our derivation of Thomas precession is the simplest existing in literature. And that's it for today. If you have any questions, leave them in the comments, I'll try to answer them. And now, let's get out of here.